how to use the ConceptBase system for modeling cyber physical systems. I'm recording this first part of this lab session, so I will put this also on either on YouTube or on Canvas. So everybody can follow me?
Yes.
Yep. Okay. So let's start. So the assignment text is this one here. Let's see whether it opens. Yeah. So the part on examination, I leave that out. So there's a little background that is discussed in more details in the lecture. We're using a so-called ontology, that is a set of concepts for cyber physical systems, and that shall be instantiated. So we make examples of these concepts in order to model cyber physical systems. In the community, this is sometimes called a domain-specific modeling language. So our ontology that we are using is also a domain-specific modeling language. We have used that in the Elvira project. That's the reason why this ontology is called Elvira taxonomy. So for the purpose of this lecture on lab, the terms taxonomy and ontology are the same. Yeah, so then I would like to move to the installation part and the use of ConceptBase. So you should have downloaded the so-called virtual appliance from this address. So let's see where that is. So that is this file. It's quite big. So once you have downloaded that, you can use the VirtualBox program that you should also install, and then import it as an appliance. So that is the user interface of VirtualBox. Maybe your looks a little bit differently. This is a rather old version, but it's basically the same. So you should use this import appliance, and then you should locate where you have downloaded your virtual appliance. That may be in your download folder. I already did that. And then once you have done that, after 5 minutes, you have this entry here. You see I have several virtual machines. So this is like a virtual computer, a virtual machine. Ubuntu 32 Pix, that is a version of Ubuntu, and we use the 32-bit version. There's no benefit for using 32 bits, but also no disadvantage of using the 32-bit version. So let's start that. Before I start, I would like to what is that? Show the settings, yeah. The settings. So there's a notion called shared folders, and I advise you to have at least one shared folder. So I use, for example, this one. You create a folder somewhere on your local computer, and then you edit using this little symbol here, the plus symbol, or you press the right mouse button and then add shared folder. And then you select that folder, give it a name, and then you should tick auto mount, that it's always available. So this shared folder is useful if you want to exchange files between your local computer and this virtual machine. For example, you want to write your report in on your local computer, and you need some text that comes from the virtual machine, or definitions, graphs, and you can use a shared folder to easily exchange that. So let's now start it up. It takes a little bit. So now you should see this desktop. That's a little bit more crowded than your version, I guess. So where is the shared folder? Here, that is here, this symbol here. And double click on that to open that. And then we see I have a number of files there. Yeah, so now let's do the first steps. There's a README file that helps you to manage the system here. All the software that you need for Lab2 is pre-configured, and that is particularly the ConceptBase system. Indeed, you have a complete development environment. So you have all the sources of the system, and you can update them and compile them. The version that you have is pretty recent. If you want to update that, you can open a terminal, and then you would type in update CV for update ConceptBase, and then it will download the latest version, compile it, and install it. It takes about 10 minutes to do so, because it's rather complex system in terms of source code. I don't have to do that, but because it's relatively recent. Now, some more information. The user account is CB, so the username is CB for ConceptBase, and the password is ConceptBase. If you want to, for example, to install new packages like text processors or so, you may need this password to install further software packages on this virtual machine. On the right side, right bottom side, you see a flag symbol. It's currently set to the US keyboard layout. I click on that, and then I get the Swedish layout. If you click again, you get the German. And that's the 3 layouts that are pre-configured. You can add, I think, more layouts for your computer keyboard. But I use the Swedish layout. Now, this is a command to start the server specifically for the purposes of the assignment. So it has all the necessary definitions pre-configured. So let's do that. I type it in by hand. CV server minus pix. So that starts a new server. Let's make it a little bit bigger. So that's the version compiled end of March. It is started in the so-called non-persistent mode. So it uses the, it has a database with all the definitions that you need for the assignment. But when you make changes, the changes are lost when you shut down the system. That is, that's how it's configured in this case, because I think it's easier for your workflow if you can start it up again, and it starts with a fresh system, so that you don't have to delete anything. So now this is running on this local host, and the port number is 4002. It's a server, and under most operating systems, these servers offer their services under a so-called port number. The default port number for ConceptBase is 4001, and here it uses 4002. So let's start now the user interface of ConceptBase. There are two of them, the graph editor and the CBIVA, that is the ConceptBase user interface in Java. And that's the one that we start with. You can double click that. And now it's connected. So you see here, the port number is 4001. That's the default port number. So it's not yet connected to this database. So let's connect it to this database 4002. So localhost is the same as this one here. It's the current host that you are working with. And when you connect, you see here in the log that it has been connected. And here you also see that the port number is 4002. So I strongly advise you to look at the connection details here, that you are sure to which server you are connected. There's another thing here. It says that the module is m_cb. M stands for module, and cb is a username. So that is an area or workspace in the database where your definitions are inserted or where you work on. The modules in ConceptBase are in a hierarchy. So there's a top level module called system, and below that there's a sub-module called home. That's the home module. And in this case of this database, this has a further sub-module called Elvira taxonomy that contains the definitions that are used in Lab2. And inside this module, Elvira taxonomy, is this MCB module. You can also see that when you press this button here at the top of the interface, that is called list current module. So let's press that. And I'll take a second. And then it shows the current content of the module. These curly brackets are comments, so it's currently empty. And the header here says what the module path is. So we are currently in m_cb, and that's a submodule of Elvira taxonomy, and that's a submodule of home, and that's a submodule of system. So these supermodules all contain some definitions that are visible in the submodules. So the submodule m_cb sees all the definitions of Elvira taxonomy, and that sees all the definitions of our home, and that sees all the definition of system, which are the system objects of defining, for example, a class and queries and all the classes that are predefined in the ConceptBase system. So let's empty that. That's this little clear button. This just clears this text window. It doesn't delete anything. It just clears the editor window. So now let's do a little exercise. Employee. We define a class employee in class. So in means an instance of class. It is an example of class. Class is also a predefined object. So we can say employee is a new object that is an instance of the known object class. We'll give it some properties or attributes. That is the term attribute here. And well, then it's pretty much like a class in Java, or so in Java, these are called instance variables or class variables, and some are instance variables, some are class variables. We don't make this difference here. So an employee has a name, which is a string. Then it should have a semicolon, and then our salary integer, and let's say works for a project. So string and integer are predefined classes for text strings and for integer numbers. Project is not yet defined. So let's try to define that. That is this button here. Tells content of Taylor's editor to the database. So the tell means insert that to the database. If it's already there, it will not add anything. So tell means, yeah, I tell you that this is true. And if you already know that, then you don't change your knowledge base. This is currently not known, so let's tell that. And we see there is an error message. This refers to a non-existing object project. So we have to define project. You might wonder why I don't define that before this, but well, it's the ConceptBase system also allows to define that after it is used. So let's say this has also an attribute budget. It's also a number, integer, and now we successfully tell that. So the yellow color here indicates that this was successful. You can also look at the log here and see, well, initially we had an error, and now the second one, the completion is okay. But you see that here as well. And you get a confirmation here as well. Good. So let's use the graph editor. The graph editor can be called from within this window. You click the name of an object, and you select display in graph editor. An alternative would be this browse and then graph editor, and then you have to type in the name of the object. But this is a bit more convenient. So that's the employee object. Let's also display the project here. And these two are connected by this, by the works for relation. It should be noted that attributes like name and salary are not distinguished from relations like works for. So this is different from object-oriented modeling languages like UML, where they make a difference between attributes and associations or relations. They are not distinguished here. Indeed, string and integer are also objects, and project is an object. Now let's look at this, and we can draw a little rectangle around them to select the two. And alternatively, you can press the shift button and then click on the two while pressing the shift button, the left shift. And then there is this function to show the links between the marked objects. Yeah, and then you see the works for association. So let's confirm that this also works for the other. So let's select all of them. And then you see that integer is also linked to them. Good, make a little break. Do you have questions? Please unmute if you have a question and just interrupt me while I'm presenting.
I have one question. Okay.
Yeah.
About the arrows.
Yes.
Is there a reason for this?
Yes. So all attributes and relations are directed. So if you look at the text here, works for is from employee to project. It is an association defined at employee, and it points to project.
So how do one construct undirected graph?
Yeah, so, yeah, you either can say that a relation is symmetric, then the reverse is also true.
Then it will be double arrowed, or will it be without arrows?
No, there are, you can have links without arrows, and we will use such links also in the power grid example. So the graphical display can hide the arrow, but essentially all links are directed. So you have to explicitly say that a certain association is symmetric, and then the reverse association is computed. It is derived from the explicit relation. Yeah, so we can make an example. So let's say knows employee. So employee knows employee. Okay, so now I have a cyclic relation knows here. It's still directed. Now I would like to have this symmetric, then I can have a rule, one. Yeah, the syntax is that you have to use a dollar symbol here. That's like a quote. And then this is using a dialect of first order logic. So for all E1, E2 of employee, so for two employees, if E1 knows E2, then E2 knows E1. Yeah, so this is a rule that derives the other direction from this node. So let's tell that, and now we have that. So let's see whether this is working. I clear that, and let's define Mary in employee without further properties at the moment, and Bill in employee, and that has somebody he knows. So knows is defined at employee, and an employee can know several other employees. So under this knows association, we can have multiple entries here. Let's say we have another employee, Anna in employee, and then we have knows two, that is Anna. So let's tell that is successful. Now let's go back to the graph. You can use the right mouse button to see some pop-up menu. And here instances means to show the instances of employee. And the first compartment here is the explicit instances. You can also have derived instances by rules, or if you have a subclass of employee like manager, then every instance of manager is also an instance of employee by deriving that, and then you would have to use all here. Good, so that's the 3 employees that we know at the moment. The green links here are instantiation links. Will look a little bit like the UML instance links. So green color means here instantiation link. So you to see which instances here. So let's do the same trick as before and show the explicit relations. So that's currently just these 2. Yeah, because we only specified Bill knows Mary and Bill knows Anna. These are directed links, but we also had the rule. So we can see outgoing attributes. Oh, something is, maybe I have to validate and update the shown object. Oh yeah. Sometimes if you make a change like this, you have to synchronize this. Don't know why this is, maybe I can get rid of that. So the outgoing attributes, no. For some reason, it doesn't show that. But the system knows that Bill is known by Mary, but for some reason, it's not displayed. So that's, maybe I have to validate it again. Outgoing attribute. Let's hide this. Outgoing attribute. No, it doesn't want me. There's a certain misconfiguration, but the system knows that. The database knows that. Good. So you make definitions in this window here, and you can visualize that in the graph window here. Once you have done a certain number of definitions, you might want to save what you have done. Yeah, we have done a bit more than this. We have also defined employee. So you can see that if you load this object, then you see the whole definition again. If you want to see everything that you have done, you press this list module button, and then you see all the definitions that have been done in a temporal sequence. So it has a timestamp here in a comment. We initially did that, and then we added the knows attribute, then we added the rule, and then we added some instances here. So we can incrementally change and update objects here. The rule was added later. Now you may want to save that, and then you press Ctrl-A to select everything, and then copy. And then under accessories, you have a text editor, gedit. It's a bit like Notepad++. And then you, with Ctrl-V, you paste it. Then you can save it maybe on desktop and give it a name like test1.txt. Save it, and then it should be here on the desktop. Double click that, and then you have the definition here. So let's, yeah. So if you if you want to work on some of the definitions, it's wise to store them in an external text file. And then if you work on it the next day, you can start the ConceptBase system and then copy and paste it from here, Control-C, Control-V, and then use the tell function to tell it. And currently it's already known, so we don't have to tell it again. Good, so that's this function. Now, another way to store your current definition is to store this graph file. This graph file is a view of the database. So it doesn't contain everything because that was not here, and also, you know, maybe some other properties like name is not displayed here. So it's a partial view of this module m_cp. You can save that, save, and then let's save it in the home directory on desktop. And let's say we call it graph1. So this will save the graph, but it will also insert all the definitions that are needed for this graph. So let's save that. And you have this new file graph1.gale. Now let's stop this all. It takes a second. So let's start now the database again. And just by double clicking on this file, it will start it up and tell all the definitions you see here to the database. And then you have your graph. So you can continue to work on that. You can, for example, right-click on this and display that in the Telos editor. And then you see everything is here. You can also press this button here, and all the definitions that we made are still here. They are in the graph file, so they are not lost. That's another way to store your definitions. So I would recommend to use both here, that you have redundant storage of that. Good. So let's look at that again. So it's localhost 4002. It's connecting to the right server here. So when we store a graph file, it also stores the connection details, that it connects to the same server. Let's stop that. So we didn't make changes, so can just stop it. Now these graph files are self-contained, self-sufficient. You can maybe see that by opening that with gedit. Now there's a lot of binary stuff here, but if you scroll down, you see that all the definitions are in this graph file. Yeah, these are definitions of the taxonomy, SCADA server, all things that we discuss in the lecture. And at the very end, you have the definitions that we made. Yeah, so these are all here. Let's stop that and start it up again. You might have noticed that I didn't start the server here in this text window. If the server is not running, it starts up its own server for this graph file. And that takes a bit longer because now all the definitions of the taxonomy have to be loaded, but besides that, it is functionally the same content here. Good. Stop it again, so don't save it, and I'll make another little break to give you the opportunity to ask a question. So, was that too fast, or what is your view? So otherwise, I make now a 10 minutes break, and I ask you to start up your own virtual machine and do similar operations that we discussed so far. If you have, after 10 minutes, I come back and then we can start with some individual help if you need that. Okay. So I would now stop the recording and we go back. We come back after 10 minutes. See you then. Yeah, welcome back. I tested a little bit this problem with the symmetric link that I had before. I had to open a new graph window here to display something in a new frame. And then it works. So you see this is the one direction and the other direction is derived. It is indicated here by this broken line here. So that's the symmetry. How you can define the symmetry of a relation. Let's stop that and also stop this one and start up our server again because I would like to show you how to define a cyber-physical system with ConceptBase. So to do so, I start CBIVA. I have to connect to our server again, 4002. Just to be sure, yeah, we are in the right module. So we are in the sub-module of Vera taxonomy. So let's do a little bit of analysis what we have in the taxonomy. In the power grid, you have all kinds of power components, and an important one is a transformer. Transformer is used to change the voltage of some electric power. So each voltage is derived from the electrical potential between two sides. So in the power grid, you have high voltage transmission lines with, for example, 400 kilovolts, 400,000 volts. That is efficient to transfer voltage over long distances. It minimizes the losses, the losses by heat energy. But households want the voltage at a lower voltage because very high voltage is very dangerous. So transformers do that. And that's an important concept. So let's see what's the definition here. So it's a definition in the taxonomy. It's a component type. It's a specialization of power grid component as these two attributes, lower voltage and upper voltage. And these rules here are not so much of interest here that are translating the definition of lower voltage and upper voltage to some other relations. So let's select that and display that in the graph editor again. So here we have the transformer object. So now always note in which module we are. So we are in our home module M_CB, and we see all the definitions in the supermodule Elvira taxonomy, and that actually comes from the taxonomy. A concept in object-oriented modeling is specialization. The key word here is ISA. So we already learned the instantiation that are for instances or examples. And the second type of relations is ISA, specialization. So we define transformer to be a specialization of power grid component. It's a subclass of power grid component. You can also visualize that. So you click on that and display the superclasses. Then you see it's a subclass of power grid component. And you can continue this chain. So that is a subclass of managed physical component, power grid component. So we all have other infrastructure networks like district heating networks that have different types of component, valves or pipes and so forth. Manage means we have later a computer, an IT system that manages that, a SCADA-like system. That has another superclass, sorry, not subclass, but superclass, physical component. So it's a whole hierarchy. And physical components has a superclass component, and that's an important concept in our ontology. And then we end with the hierarchy. The most generic concept is thing. So everything is a thing in the ontology. But components are special. We have other subclasses, for example, cyber component. So cyber components will be, for example, computer programs, databases, configuration files, but also data flows and so forth. So everything that is bits and bytes that are either at rest or that are doing something or flowing from A to B. That's a cyber component. We have also another subclass of physical component. Let's see. IT component. So we have IT component, and that later stands for all kinds of hardware that we have. Computers, but also routers, switches, and so forth. So, and data lines that are connecting IT components. So that is a very rough introduction into the taxonomy. It's called a taxonomy because it's here a tree structure of concepts. If you have a transformer, then it's also a power grid component. It's also a managed physical component, also an instance of physical component, and thing. So now let's start to model a very simple power grid. And in the power grid, we have, for example, so-called bus bars. The bus bars are used to select several power lines or several power grid components together. It's like a piece of copper, and then you connect the other components to this piece of copper in order to connect them. So let's tell that that's successful. In our graphical view, we have a bus bar here. So it's also a power grid component. So we define here two bus bars, BB11 and BB12, as instances of bus bar. And then we define a transformer, TT1, that has a power connection to bus bar 11. So power connection is another cable that connects these two components. So let's delete this one and display that in a new window. That's a bus bar. In this database, we have some graphical types assigned to power grid components. The bus bars are black rectangles with white color. Now we also have the other bus bar. Like this. And we have the transformer. The electrical symbol are two circles overlapping each other. That's the symbol of a transformer. Now we have a power connection here. Let's select all of them and then draw this line. So now you notice this has no arrow. It's a directed link, but the graphical symbol for that is just a line without an arrow. So it goes from TT1 to BB1, but only that one is displayed. This is defined to be symmetric in the taxonomy. So if you would look here at outgoing links, maybe I have to make that bigger. Outgoing, and then, oh, something is odd here. The graphical display is power connection. Yeah, that's something with the user interface is not working. This TT1 has a power connection to BB1, but the other way is also true. Well, let's see whether I can. No, I cannot do that. So let's also connect busbar 1, 2 to that. So we have a second power connection. We give a running number PC2 here. That's busbar underscore 1, 2 and tell that. And now we have here a transformer between two bus bars. So this could, here the electric power could come from outside and it's transformed, and maybe here we have some households connected to that. So let's define a power line. In power line with power connection EC1. The numbering is always local to the object. So it's to bus bar score 1, 1, and tell that and display that. That's a symbol for a power line that has some length. So we can see that is connected here. So the electricity may come from here and then it is directed to this transformer. Maybe we have another power line PL2 that is also connected to that. And connect to that, and then maybe that goes to another location where we have another bus bar. So this is typically, these are typical components for a so-called substation. If you are driving in the countryside, or then you sometimes see some cables going into a an area where you have big transformers and a lot of power lines that are connecting the components. There, the electricity is transformed, and then there are other power lines that go to, for example, households that start from here and then go to households. This may go to another substation. So then we have a substation here. So that's what I wanted to show. And I would like now to, I will stop the recording and I welcome questions, and then we can go to breakout rooms to provide individual feedback.